Hi dear students, hope you all are fine and had gone through my earlier lecture on autocorrelation. Today we are extending our discussions a little bit more. As you are aware, we had divided the lecture into 4 parts, and this lecture is the second part of the topic on autocorrelation. In the first part, we had discussed about the definition of autocorrelation, what are the possible patterns of autocorrelation, and what are the important reasons for autocorrelation. Today, the scope of our lecture is around the question of estimation in the presence of autocorrelation. Also, examine the consequences of using ordinary least squares in the presence of autocorrelation. Finally, we will discuss about the best linear unbiased estimation in the presence of autocorrelation. Most of the inputs I received for this lecture is from the basic econometrics written by Damodar Gujarati. I also referred the introductory econometrics written by Jeffrey Woolrich. Use of some online discussion forums also sought wherever required. So far, we have discussed the definition of autocorrelation and what are the reasons for autocorrelation. Now we turn our attention to a much bigger question. What happened to OLS estimators and their variances if we introduce autocorrelation in the disturbances while retaining all other assumptions of the classical model? That is, the error term follows zero mean and homoscedastic variances, but exhibit autocorrelation. What will happen to the estimators and their standard errors? We use here a simple two-variable regression model to explain it. Let us take our model as yt is equal to beta 1 plus beta 2 xt plus ut. As a starting point or a first approximation, one can assume that the disturbance term or the error term are generated by the following mechanism. That is, ut is equal to rho into ut minus 1 plus epsilon t. Rho into ut minus 1 plus epsilon t, where rho is known as the coefficient of autocovariance, or it is the Karl-Pearson coefficient of correlation between ut and ut minus 1. It lies in between plus and minus 1. You can recall the Karl-Pearson's method of calculating the coefficient of correlation. The equation for it is given in the text box. It is obtained by dividing the covariance of ut and ut minus 1 by the product of their standard deviations. The equation is rho is equal to expectation of ut minus expectation ut into expectation of ut minus 1 minus expectation ut minus 1 divided by square root of the variance of ut into square root of the variance of ut minus 1. So we in the beginning we assume that there are two assumptions we retain. Two assumptions of classical linear regression model are retained here. The first assumption is zero mean, that is expectation u is equal to ut is equal to 0. The second assumption is homoscedastic variance, that is variance of ut is also equal to variance of ut minus 1. So if we retain the first assumption, that is zero mean, expectation ut is equal to 0 for every time period, then the numerator part of the equation described above become simply expectation of ut into ut minus 1. And if we assume that the variance of ut is same for every period, that is homoscedastic variance, then the denominator parts also becomes variance of ut minus 1 or variance of ut. That means the square root of the variance is standard deviation, and the standard deviation of ut into standard deviation of ut minus 1, when ut is equal to ut minus 1, it become variance. So therefore simply we can write rho is equal to covariance among ut and ut minus 1 divided by variance of ut minus 1. Returning to our example, ut is equal to rho into ut minus 1 plus epsilon t, where epsilon t is the stochastic disturbance term, such that it satisfied all the standard Euler's assumptions, namely expectation of epsilon t is equal to 0, variance of epsilon t is equal to sigma square e, and covariance of epsilon t and epsilon t plus s period is equal to 0. The error term with all these properties is often known as white noise error term. Thus, in the equation ut is equal to rho ut minus 1 plus epsilon t, the value of the disturbance t term in period t is equal to rho times its value in the previous period plus purely random number term. This scheme is also known as Markov first order autoregressive scheme, named after the famous Russian mathematician Andrei Markov. It is simply called as first order autoregressive scheme, usually denoted as AR1. Why this model is termed as autoregressive? Because the equation can be interpreted as the regression of ut on itself, lagged by one period. It is first order because ut and its immediate past values are involved, that is ut minus 1, where the maximum lag is 1. If we have the model where ut is equal to rho 1 into ut minus 1 plus rho 2 into ut minus 2 plus epsilon t, it would be an AR2 or autoregressive of second order scheme. The rho, that is coefficient of autocovariance, can also be interpreted as the first order coefficient of autocorrelation or the coefficient of autocorrelation at lag 1. An AR1 model is autoregressive process 1 in which current value is based on the immediately preceding value, while AR2 process is 1 in which the current value is based on the previous two values. Given the AR1 scheme, it can be shown that variance of ut is equal to the homoscedastic variance of the white noise error term divided by 1 minus the square of the autocorrelation coefficient, and the covariance between ut and ut plus s, covariance between error terms in s period apart, is equal to the correlation between error terms in s period apart into the homoscedastic variance of the white noise error term divided by 1 minus the square of the autocorrelation coefficient. Note that one important property of the covariance and correlations here. The covariance between ut and ut plus s is also equal to the covariance between ut and ut minus s, and correlation between ut and ut plus s is also equal to the correlation between ut and ut minus s. The proof of the above equations, that is the proof of the way variances and covariances are computed, are given in this slide. Kindly go through the procedures involved in a step-by-step manner. Take your time and get a thorough understanding on it. The equations are self-explanatory. Since rho is a constant between minus 1 and plus 1, the equation 12, that is variance is equal to sigma square divided by 1 minus rho square, shows that under the autoregressive of order 1 scheme, the variance of error term is still homoscedastic. But the error term is correlated not only with its immediate past values, but its values several periods in the past. It is important to note that the absolute value of rho is less than 1. If, for example, if the absolute value of rho is equal to 1, then the denominators of the equation 12 and 13, that is, it's showing the variance and covariance. The denominators become 0, and therefore the variance and covariance listed above are not defined. If absolute rho is less than 1, we say that the AR1 process given in equation ut is equal to rho ut minus 1 plus epsilon t is stationary. That is, the mean, variance and covariance of ut do not change over time. If absolute rho is less than 1, then it is clear from the equation 13 that the value of covariance will decline as we go into the distant past. One important reason that we use the autoregressive order 1 process is not only because of its simplicity compared to other higher order autoregressive scheme, but also because of its use in many applications. Now let us consider our two variable regression model, that is yt is equal to beta 1 plus beta 2 xt plus ut. We know that the OLS estimator of the slope coefficient, that is beta 2, and the variance are beta 2 hat is equal to sigma xt yt divided by sigma xt square. This is nothing but covariance between x and y divided by variance of x. And variance of beta 2 hat is equal to the homoscedastic variance of the disturbance term divided by variance of the independent variable, that is sigma square divided by sigma x square. Now under autoregressive of order 1 scheme, it can be shown that the slope coefficient, that is beta 2 hat, remain the same because we are computing it from the x and y only. But the variance of the estimator obtained by that is variance of beta 2 hat under AR1 scheme, that is obtained by multiplying the variance of beta 2 hat under ordinary least square method into an additional component which is showing or which catching the all effects of autocorrelation. That is, variance of beta 2 hat under autoregressive of order 1 scheme is obtained by multiplying the variance of the OLS estimator with an additional term showing the effects of autocorrelation. And this additional term is obtained by adding 1 plus 2 into rho, that is autocorrelation coefficient, into sigma xt into xt minus 1 divided by sigma xt square. This is nothing but the simple correlation coefficient between two independent variables. One variable in the current period and one variable is the just preceding period. Again plus 2 into rho squared into again simple correlation coefficient between independent variable x variables in two periods apart, and it will continue so on. So in short, we can summarize it as variance of beta 2 hat under autoregressive of order 1 scheme is obtained by multiplying the variance of beta 2 hat under OLS method with an additional term. That additional term is 1 plus the effects of autocorrelation. A comparison of variance of beta 2 under AR1 scheme with variance of beta 2 hat under OLS method shows that the former is equal to the later times a term that depends on rho as well as simple autocorrelations between the values taken by the regressor or independent variable x at various lags. In general, we cannot foretell whether variance of beta 2 hat is less than or greater than variance of beta 2 hat of order AR1 scheme. If correlation coefficient is 0, the two formula will coincide. Also, if the correlation among the successive values of the regressor are very small, the usual OLS variance of the slope estimator will not be seriously biased. But as a general principle, the two variances will not be the same. Thus, a conclusion can be derived from this analysis is that a blind application of the usual OLS formula in the presence of autocorrelation to compute the variance and standard errors of the OLS estimators could give seriously misleading results. Suppose we continue to use OLS estimator beta 2 hat and adjust the usual variance formula by taking into account of the AR1 scheme. That is, we use beta 2 given by the equation sigma covariance xy divided by variance x square, but use the variance formula of beta 2 hat under AR1 scheme given by equation 17. That is, we just seen that variance of beta 2 hat of the OLS estimator multiplied by the correction factor for the autocorrelation. It is to be noted that beta 2 hat is still linear and unbiased. Therefore, we do not require the assumption of no autocorrelation like the assumption of no heteroscedasticity that we have seen earlier to prove that beta 2 is unbiased. But beta 2, although linear and unbiased, it is not efficient as it does not have the property of minimum variance. Now let us summarize the above discussion by pointing out all the consequences of using OLS in the presence of autocorrelation. We have already seen that the case of heteroscedasticity, the OLS estimators are linear, unbiased, as well as consistent and asymptotically normally distributed, but they are no longer efficient. That is, they do not have the property of minimum variance. In the same way, in the presence of autocorrelation also, the OLS estimators are linear, unbiased, consistent and asymptotically normally distributed, but they do not hold the property of minimum variance. Now the question that should be addressed is, what then happens to our usual hypothesis testing procedures if we continue to use the OLS estimators? Here we have two cases. Let us discuss each case separately. First, you can see OLS estimation by allowing for autocorrelation. Here we already seen that our slope estimator, that is beta 2, is not blue. And even if we use variance of beta 2 under AR1 scheme, the confidence interval derived from them are likely to be wider than those based on generalized least square procedure. As observed by Jan Pimenta, an American econometrician and a statistician, this result is likely to be the case even if we increases the sample size indefinitely. That is, beta 2 is not asymptotically efficient. Then what is the implication of this finding for hypothesis testing? We are likely to declare a coefficient of a particular explanatory variable statistically insignificant, that is not different from 0, even though in fact it was significant. We are likely to declare a coefficient of particular explanatory variable statistically insignificant even though in fact it was significant. You can see the differences of both approaches in the figure given here. You can see the 95% confidence interval of OLS under AR1 process and GLS, assuming that true beta 2 is equal to 0. Consider a particular estimate of beta 2. Say in the given figure it is B2. Since B2 lies in the OLS confidence interval, we could accept or we do not reject the hypothesis that 2 beta 2 is 0 with a 95% confidence. But if we are to use the correct GLS confidence interval, we could reject the null hypothesis that true beta 2 is 0 for beta 2 lies in the region of rejection. Therefore, in order to establish confidence interval and to test hypothesis, one should use GLS and not OLS, even though the estimate is derived from the latter are unbiased and consistent. Now, let's consider another case. Here, the situation is potentially very serious. If we not only use OLS estimator beta 2 hat, but also continue to use its variance obtained by the equation, that is sigma square divided by sigma x square. That is, we completely disregard the problem of autocorrelation. We mistakenly believe that the usual assumption of the classical model hold true. In such situation, a number of errors may arise because of the following reason. First, the residual variance of the estimator, that is sigma hat squared, is equal to sigma u hat squared corrected by n minus 2 degrees of freedom, is likely to underestimate the true homoscedastic variance of the residuals. That is, sigma hat squared is likely to underestimate the true homoscedastic variance. As a result, we are likely to overestimate r square. That is, our calculations on the explanatory power of the model may go wrong. Even if the residual variance of the estimator is not underestimated, variance of beta 2 hat may underestimate variance of beta 2 hat of AR1 model. That is, we disregard autocorrelation. As a result, our estimation of the variance underestimate the true estimate of the variance under autoregressive of order 1 scheme. Therefore, we cannot rely upon the usual T and F tests of significance. They are no longer valid, and if applied, they are likely to give seriously misleading conclusions about the statistical significance of the estimated regression coefficients. To understand these things in a much better fashion, let us consider the two-variable model. Under the classical assumption, the estimated residual variance sigma hat squared is equal to sigma u hat squared divided by n minus 2. This provides an unbiased estimate of the true population parameter sigma square. That is, estimated sigma hat squared is equal to sigma square into n minus 2 by 1 minus sigma into minus 2 rho r divided by n minus 2. So we have already seen that rho is the autocorrelation coefficient, which is obtained by dividing the covariance among two successive error terms by the homoscedastic variance of the residual term. Similarly, here r is also interpreted as the simple correlation coefficient between two successive values of the explanatory variable x, as shown by the equation above. It is also obtained by dividing the covariance between successive values of the explanatory variable by their variance. If rho and r are both positive, the usual residual variance formula on average will underestimate the true sigma square, true population parameter. That is, the estimated variance is less than the true variance. The estimated variance, in other words, the estimated variance is biased downward. This bias in estimated variance will be transmitted to variance of beta 2 hat. Why? Because in practice, in order to estimate the variance of beta 2 hat, we use the formula sigma hat square divided by sigma x square. Another important point that we should keep in our mind is, even if sigma square is not underestimated, variance of beta 2 hat is a biased estimator of variance of beta 2 hat under AR1 scheme. Therefore, if rho, the autocorrelation coefficient, is positive, which is true in most economic time series. And if the x's are positively correlated, this is also true of most economic time series. Then it is clear that variance of the estimator obtained by ignoring the autocorrelation is less than the variance obtained under the AR1 scheme. Once again, if rho is positive and x's are positively correlated, then it is clear that variance of the estimator obtained by ignoring autocorrelation is less than variance obtained under autoregressive of order 1 scheme. That is, the usual OLS variance of beta 2 underestimates its variance under AR1 scheme. Therefore, if we use the OLS estimator variance of beta 2, we shall inflate the precision or accuracy of the estimator beta 2. As a result, in computing the t ratio, we know that t is equal to beta 2 hat divided by standard error of beta 2 hat. So in computing t ratio, we underestimated the standard error and therefore overestimated the t value, and hence the statistical significance of the estimated beta 2 is also affected. Now, what should be the best estimator in the presence of autocorrelation? Let's assume a two-variable model with the AR1 process. We use GLS, generalized least square method, to derive the blue estimator of beta 2. Recall our previous lectures on the GLS, OLS and maximum likelihood estimation of parameters. In both ordinary least squares and maximum likelihood approaches to parameter estimation, we made the assumption of constant or homoscedastic variance. That is, the variance of an observation is the same regardless of the values taken by the explanatory variables. There are many real situations in which this assumption is inappropriate. In some cases, the measurement system used might be a source of variability. Other times, this occurs when errors are correlated, that is, when there is autocorrelation. Also, when the underlying distribution is continuous but non-normal or skewed distribution, such as log normal distribution or gamma distribution, etc. The underlying distribution is continuous but either skewed or log normal or gamma distribution. Then the variance is not constant. The OLS estimate in OLS method, we assume that the variance of the observation is unrelated to the mean. But in many cases, variance is a function of the mean. If we have the case in which the errors are uncorrelated but have unequal variance, that is, the assumption of homoscedasticity is violated, but the assumption of no autocorrelation is satisfied. In this case, we use a simple weighted least square method, where we give less weights to observation coming from population with the larger variance and give more weight to observation coming from population with the smaller variance. But if you have a case in which both the assumptions are violated, that is, the assumption of no heteroscedasticity and the assumption of no autocorrelation are violated, we should use the generalized least square method. GLS was first described in 1934 by Alexander Aitken, one of the New Zealand's most eminent mathematicians. Here we usually transform the original variables in a way that the transformed variables satisfy the assumption of classical model. We apply to OLS to the transformed variables. In short, GLS is OLS on the transformed variables that satisfy the standard classical least square assumptions. The estimators thus obtained are known as GLS estimators, and these estimators are blue. Let's assume a two-variable model with the AR1 process. We can show that the blue estimator of beta 2 is using the following expression. Beta 2 is equal to sigma xt minus rho xt minus 1 into yt minus rho yt minus 1 divided by sigma xt minus rho xt minus 1 all squared plus c. This is the usual covariance divided by variance formula, but we allowed the autocorrelation coefficient rho explicitly incorporated into the model. C is the correction factor that may be disregarded in practice. The subscript t now runs from t is equal to 2 to n. The variance of the estimator can be obtained by another equation, that is variance of beta 2 is equal to sigma square divided by sigma xt minus rho xt minus 1 all squared plus d. Here is also d is a correction factor that may also be disregarded. The superscript GLS in both estimators denote that the estimators are obtained by the method of GLS. The GLS estimator of beta 2 given in equation, this equation incorporates the autocorrelation parameter rho in the estimating formula, whereas the Euler's formula beta 2 hat is equal to sigma xt yt divided by sigma xt square. Simply neglect it. Therefore, this is the reason why GLS estimator is blue. It has the property of minimum variance and therefore the estimator is efficient. Hope you all enjoyed the session. I request you to listen this class as much as you can. Prepare notes out of it and get ready for the upcoming exams. As I mentioned earlier, we have 2 more lectures to go to finish our discussion on autocorrelation. The third and fourth part of this lecture series will be available to you shortly. Kindly wait for it. If you need any clarification on the topics covered here, kindly message me. Thank you again for your support and cooperation.